Okay, so let's see. So first off, many thanks for well, allowing me to be here and the invitation. Of course, I learned quite a bit already again over the past few days, which is great. Thanks, with a little bit of irony, also for the question I was asked to address, which is a near mission impossible in some sense. Right, that was like, okay, please review spin decomposition from, let's call it existing data. So that can be a very, very, very long talk, or it could be a very short talk, either way. And in the end, thinking a little bit about that, I just decided to do something slightly different and just turn it into a couple of comments, which I hope will fit to some of the discussions we had over the past 2 days as to where impacts could be. And also make a couple of comments as to what is recently coming out of the RIG-SPIN program, and specifically the STAR experiment. That's in a way a bias. It's natural to me. I'm part of STAR. I've been part of STAR for quite a while, as many of you know. But I think we're making a real impact at this point that is leading actually to truly new insights as well. So hence a slightly different title than you may have expected. And look, I mean, in thinking about this charge, I mean, I can put up maybe the most ridiculous chart, which you nevertheless will find in nearly every single textbook, right? So at entry level, at least, it seems to me still that all textbooks kind of start with a proton as 2 up quarks and 1 down quark. And maybe that's all very pedagogical and nice. No one in this room would think like this in the end. But at the same time, we haven't really rewritten these textbooks, right? So maybe that answers already part of the question, as in maybe we're just not there in any way or form yet. I mean, let's take a slightly alternative view, and maybe a view adopted by many of our high energy minded friends. That, well, what is actually a proton? It's kind of this unseparated beam of quarks, gluons, right? I mean, so truly Feynman-like picture. And of course, then if you're talking with your high energy friends, they also will think about maybe structures beyond quarks in the end. Now, it's hard to argue with success, and this certainly has given us one of the most, well, robust, I would say, means of quantifying a vast number of observables in hard scattering. It has theoretical foundations that are well established at this point. But it's also in a way quite disappointing that, I mean, how can it be almost, right? I mean, that we have this semi-boring system without correlations among the partons, where we just know that the world is really quite different. As in, well, the nucleon is bound. It's a bound system, for example. And actually, it's quite heartening to me that by now we are starting to see quite a few high energy physics observables that actually don't follow this idealization at all. Ridges everywhere. And I think, personally, I actually look at the spin problem, if you wish, or the spin puzzle, in a very similar way. In one way or other, you cannot escape correlations if you need to end up with a spin 1/2 object. Well, what is the task ahead then? I mean, look, we had a bit of discussion and we had some fun with each other, I think, also in sort of asking like, well, where should we go? What can we compare and what not? Well, in the end, of course, we have to push the envelope of any theoretical framework to its utmost limits and maybe step beyond them to see where it breaks down. But the end game, as an experimentalist, I think, has to be that we need to arrive at meaningful accuracies, right? And that is in parts also about impact. And yeah, what I find troublesome is that at times we sort of reject insight, even though maybe it's an approximation, and it could be a not so good approximation here or there. For reasons that are maybe not so good. Maybe it's better if we quantify and then compare. So, okay, of course, this figure came up several times as well, and I stick it in here again on purpose, Because look, would we do that today, right? I mean, it seems today that we would spend quite a bit of time arguing, like, well, what is the uncertainty on that LS-Jaffe value, for example? Are these X ranges really correct? I mean, well, many questions. Are these data points at different values of Q squareds, etc.? Still, this is probably one of the key reasons why we have this workshop at all. Well, the outcome, I mean, was of course just the difference of these central values taking into account these experimental uncertainties, but nothing else. That sort of gave this insight, well, the sum of quark and anti-quark spins contribute little to the proton spin, and then also that strange quarks are negatively polarized. Of course, that required follow-up, but maybe the first thing is that you can ask, well, how did this come about? And at that time, that was largely leading order. So how does it come about? Well, the spin structure function, of course, you can expand it. And yes, we know now how to do that in much higher order as well. I will stick to this order for reasons that will probably be clear in a little bit. Well, I mean, you have, like in the unpolarized case, of course, this sum of quark distributions with charge weights or charge squared weights in front of it. You could reorder this in terms of two combinations that involve differences and one that involves a sum. And then the unique insight, of course, comes from this one. And the other insight, I mean, just over projection, so become 5 matrices if you wish, they both come from neutron or well, electroweak decays of neutrons and hadrons. Well, okay, so then how does this totally come about? If you set this term to 0, of course, these are identical and you have a prediction. Great, fantastic. In all of this, of course, if you need to integrate, and you need to integrate down to 0, there's just no substitute for energy in the end. And x, the lower value of x matters. It goes as 1 over square root of s, as most of us know, but we often like to forget in the sense of our extrapolations. Well, okay, so where are we today with this, right? I mean, I think experimentally, through symmetries, if you wish, I mean, of course, we could do this for both the proton and the neutron. This actually is confirmed from deep inelastic scattering data directly to about 10%, which is great, and we'll see that. This second part, this term is known from weak neutron to proton decay combined with actually a single measurement of sigma to neutron decay. Yeah.
Why have the delta 1? Is it first order?
The first moment.
First moment.
Yeah, it's just shorthand, doesn't matter.
Okay.
I mean, look,
First moment, yes.
I don't want to dwell on this.
Yes.
I was discussing it with
Oh, okay.
Yeah. Look, I mean, you need some notation. I should have probably mentioned it explicitly. I'm only doing this, by the way, not to well, give something truly trivial, but actually I think there are a few points in there numerically that get to these accuracies and where impact might actually be had by combining different fields. And given that this is an informal workshop, or at least that's how I look at it at the moment, that's the way I want to go about it. Okay, well, look, so fine, right? I mean, if this term, so this first moment of strange quark distribution is 0, then of course this is a prediction in the end, because these two I could obtain from decay values that at the time had been measured, and that's how you get this central value. Note again that, of course, the uncertainties in those couplings, we call them couplings, were not propagated at the time at all, okay? And questions about symmetries were not really asked, or symmetry breakings were not really asked. Nevertheless, we just proceeded, of course, because we have an interesting effect. So you can turn that around, right? And you can ask yourself, like, well, okay, so if I don't really believe in SU3 symmetry, can I recover actually this LS-Jaffe value? Right? Well, yes, you could. And that's actually an easy numerical thing to do. Of course, the measurements do not depend on external measurements or measurements that are external to the deep inelastic scattering measurements. So in other words, whatever the value of this constant is, it will not change the first moment of the measured integral in any way or form. That derivative is 0. You take the LS-Jaffe value, so this expansion here, the total prediction is 5 over 36, which means that you would need an A8 taking sort of central values of about 0.2 plus or minus 0.1. If you compare that with uncertainties, and where uncertainties I then take a scatter of, let's say, A8 values in the literature, it's actually below the values you find. I think they go as low as about 0.45 or so, where the central value is 0.59. So it's a sizable, potentially a sizable effect, but this effect is actually huge, starting from central values. Of course, the uncertainties are also very, very large, and in such a thing, it's a straight propagation in the end. Maybe that's actually an opportunity. Well, okay, so what happened afterwards is, of course, numerous experimental follow-ups and many, many questions. And as Werner articulated much more eloquently than I do, among the early attempts was actually, well, this one, which we all know in the end, which of course appears kind of as a higher order thing. However, since it involves delta G, alpha S times delta G would evolve as a constant. So numerically, it would appear the same order, if you wish, or it could persist at an order lower. Well, okay, if you do that, you do the same trick like with alpha 8s, with A8s. What you get is very, very large polarizations for typical scales, like factors larger than the nucleon spin itself. So that's of course a super exciting system at that point. Because if you do buy that a proton stays a spin 1/2 object, you truly need huge compensating orbital momenta to actually drive you back to this value of 1/2. Now that's quite a proton, right? As a ground state object with huge orbital momenta, vast gluon spins, cool. How about modeling that? Well, I mean, of course, it doesn't start or stop there. There are many other attempts, unmeasured regions at low X, where undoubtedly new phenomena sooner or later will show up, could play a role. They could be numerically relevant. Yeah, depending on where you put your belief as to where that should set in and how you would fit that, of course, you can arrive at very, very different conclusions in the end. Now, we've also learned that low X is difficult to assess, for example, from lattice QCD. So we need different tools. We're waiting for your talk, Yuri.
One more thing.
I can do that. Sorry. Well, okay. So look, let's go back briefly to numerics, right? I mean, this part, I mean, while it's written for the proton, if you go for the neutron, of course, these two split balance and isospin symmetric system, as you all know. That means that in experiment you can do this also, but in practice it's hard to come up with 3 neutrons, so you need to do that over neutron targets or helium-3. Helium-3 has this nice property that the protons are, proton spins are, they typically add up to 0, so it's in effect, let's say, a heavy polarized neutron target, maybe. The neutron has a complementary nice feature if you look at it, in that you actually get more direct sensitivity to these parts. Of course, if you're really after just getting a neutron, helium-3 is by far preferred over deuteron, but not in all cases are you after the neutron. Since this came up in the discussion, I thought I would just put it in here. I mean, for an experimentalist, it would seem very, very trivial, but look, we all have that things are very, very trivial, except to your friends. So look, experimental precisions in these sort of quantities, they can be matched. I mean, you can adjust your timing and all of it, as in the duration of your own period. Energies in fixed targets are per definition the same, but that's not the case in the case of the EIC, where you actually need to accelerate these beams. So the energy reaches are different in the case of protons and neutrons, no matter whether you would get them over deuterons or over helium-3. That's just a charge over mass ratio in the end. Nevertheless, doesn't matter. Maybe more importantly, as precisions go up in all of these existing combinations of different targets, the precision is thought to be not such that we need to worry too much about nuclear effects. And maybe looking ahead to an EIC, we should revisit that. Precisions will go up. The handling of nuclear effects and also measurement of many of them will actually become a task at these precisions. Well, okay, so now let's go for this check, right? This check of the Bjorkenson. So here I picked just a recent example of data, and data that extends to the smallest values of x, in the case of well, the neutron, or neutron, if you wish. So what you see on the left-hand side is a compilation of data with the red points by compass, so the ones that go from lowest x and highest q squared, and complement with the SMC data that are less precise. And then in this corner of the smaller x and smaller q squared values, you see a number of fixed target measurements. So this is a fairly up-to-date compilation of that data. And of course, what is nice about it is that it does give a reasonable harm already in q squared. That is, you can start to investigate actually what it means to have, well, scaling violations also from this data. So you can make QCD fits to it, even though modern QCD fits have gone well beyond. So what it also means is that finally one can come up with, currently, with plots like this one, which integrates the same EMC curve for the neutron, where you actually take into account these QCD effects. And of course, well, we also now know the predictions much, much better, but the game is not longer about directly comparing these quantities. It's rather arriving at, well, tests of some of your underlying assumptions, one of them being the Bjerkhoff sample. So you see here this convergence, qualitatively very, very similar to the proton, of course. Then in terms of this proton moment, this proton minus neutron moment, so Bjerkhoff sum, the central value is 0.192, and for those who prefer to think in terms of GA or GA over GV, that value is consistent with the value from neutron decay. So, well, the factor 6 is in between here, right, between these two, and then the 10% further reduction is actually directly a QCD effect. That's actually somewhat larger, let's say, than the uncertainties that come from compass. So one way of looking at this is that you not only get the normalization, but actually you have a start of the running at relatively low energies. That by itself, I think, is actually important as well. Okay, so to the second piece, here, I'll just pull it out because I think we're still quite naive in how we do this. This value of AA, right, 3F minus D. I said that this is known from weak neutron to proton decay, and it's combined then with sigma to neutron decay. Yeah, sure, there are a few other measurements, but if you look at them, and you look at the combinations you in the end need, which are, well, F and D, or the ratio of F over D, it's really determined by only two measurements. Well, this one is infinitely precise, though not necessarily consistent in time. The other one is actually quite heroic measurement of sigma decay, the Fermi-lab beam line. And then if you look at the other measurements, in one case the precision could be slightly better. However, because you're angled in a different way, so you're not in an orthogonal way solving the system of equations, actually you completely lose your sensitivity. So this measurement, while interesting by itself, for this purpose actually is completely irrelevant. Further measurements that have been done at some point with KTEF actually have not changed that picture at all. Well, so what you have for this entire constant of 0.59 is actually a 1 + 1 experiment determination. And by 1 I mean something which is super precise from a number of sources, and then one single experiment that totally determines what this is. Well, there's no hope of doing that better without mounting a new experiment in any way or form. And furthermore, in many of well, the easier, let's say, experimental extractions, you see that SU3 breaking is largely ignored, the possible size of that. Now, lattice QCD has, whatever way you want to phrase this, it has, I think, recently made quite a bit of progress in precisely benchmarking to this value, if that's how you want to look at it. Maybe that's a renewed opportunity in the end. Okay, I don't know how that numerically works out. I know that it has been started, but I don't know about the 2% precision that one currently has achieved with this GA value. So I'd be interested to learn. Okay, so now as to spins, of course, well, again, this is where the 0.3 comes from. It's indeed a modern extraction of the data, of data directly. I picked here data that just covers a wide range in X. Now, okay, this was all inclusive, and you can ask questions about the decomposition. At the moment, it is certainly true that semi-inclusive deep inelastic scattering data drive the DIS flavor decomposition completely. They completely dominate it. That's a long and convoluted history, I would say, experimentally even, but also phenomenologically, of let's say, differences of opinion, but also differences of fact in use of fragmentation functions, for example. Okay, so let me now switch just gear to Rick's spin. This is there for completeness, because I've noticed in many talks actually that to the insider community it's completely straightforward if you talk about, well, RON 9 or 13 or whatever. To the outsiders, it means absolutely nothing. So this is the current status. What you see is a figure of total integrated luminosity, and with that kind of figure of merit, in the polarizations, yes, they increase, but the increases are relatively modest. Then what is done is with these dashed lines, it's the lower, typical lower energy at RIC, so 200 GeV center of mass, 100 GeV beams. At 250 GeV, those are these continuous lines. Okay, so then what you see is a progression with years, and of course, well, the key data sets at highest energy are 2013 and 17, which in star were split up in about equal total luminosities for longitudinal and transverse data. So the figure of merit for transverse data is actually higher than that for longitudinal measurements, given that one goes as p to the fourth and the other one is p squared. So you can do the same thing for 200 GeV, and actually you will end up with data sets that are quite matched. Is there a comment or? Okay. Well, okay, so this we've seen, and we've also seen how it got propagated in DSSV as well as PDF, NMPDF fits, right? And it's good that actually different, what I think are different approaches and also different use of data sets do lead to well, numerically very, very similar values, of course, over a very finite range in X. Okay? The range covered by the data. So, what is also quite good and often overlooked with the previous earlier data set, that actually separating this into pseudo-rapidity regions already provides initial sensitivity to kinematics, which is quite important. So, well, so it leads to a positive delta G, value of about 0.2 h bar, of course with large uncertainty still. Now I like this figure quite a bit. What in my mind it really shows is on this axis, let's call it the experimentally assessed part of delta G, and in this axis the dominant part of an extrapolation. So, well, what is the picture then? Where you start out with essentially an unknown landscape from deep inelastic scattering data. You bring yourself to, well, a landscape where star or big data has actually led to, you know, positive values with an uncertainty that is admittedly large, but at least such that you can talk about it in a meaningful way. Of course, at the same time, you see that very, very limited progress is being made in the unmeasured region. Well, so what does that mean in terms of decomposition? Well, among other, it means that it's easy to hide a unit of h bar or so in the unmeasured region, just looking at, well, the size of this vertical blob. So what does it mean from an experimental point of view at RIC or at STAR? Of course, one wants to get to better precision, right? I mean, obviously, you want to narrow this down further because that's what you can do. And it may be a while before you can do that better. That's mostly done through renewed measurements of jets, of course. You want to get to sensitivity of underlying kinematics because if you resolve in this range the kinematical form, you would expect that at least for part of the unmeasured region, it would at least continue in in a way. In other words, measuring or resolving an X-dependence here should lead to somewhat reduced uncertainties in extrapolations, or at least more confidence in extrapolations. Then you want to obviously also get to sensitivity to smaller values of X, smaller than this 0.05 here. The way to do that is with 500 GeV data and with forward acceptance. Now, what is great news is that STAR is actually releasing, or has published, and is continuing to do so, a wealth of data addressing each of these aspects. We also have what I think is a good plan, and certainly an endorsed plan by PACs, for forward instruments that actually drive us to smaller sensitivities to smaller X values. That's a talk by itself. I don't want to go there. Truth in advertisement is that a plan is not the same as approval in the end at funding level, at least not as of today. That also probably means that some of you will hear a bit more about this sooner or later, because, well, if you want to do this, we may need a little bit of support in STAR from outside our community, if you wish. So let's have an early glimpse at some of this data. This is published. So what you see here is very forward data. Pseudo rapidities of well, 2.6 to about 3 and 3 to about 4 of forward measurements in our FMS compared with uncertainty bands. Right, so these are the bands for the two fits. If you well, central values, dashed and continuous, and these are the data points with their systematic uncertainties. Now, if you look at this, of course, you could think about like, okay, these uncertainties look actually somewhat large compared to the bands. Yeah, maybe so. Of course, you could always read in the data. What that means is that such a measurement is not a silver bullet, as in you immediately nail the low X behavior. But it's also quite clear if you have a number of points, you actually do constrain in this region. Set aside that this region had not been measured before in any way form. Okay, this has a continuation looking ahead, namely through correlation measurements, where two of these particles, in the best of cases, will go in that very, very forward acceptance. Another matter that goes at this X-dependence is over our dijet asymmetries. So dijet asymmetries are at least at Born level kinematically complete. So you have the X-dependence in the end. And what you see here is, in some sense, the equivalent of this RAN9 inclusive jet, or the analog of the inclusive jet measurement. You see for two pseudo-rapidity configurations, well, the dependence is a function of the invariant mass. You observe the symmetry. And then again, uncertainties on the bands, same way, data are the lines, and the boxes indicate the size of systematics, and compared with, again, the two PDF fits with their uncertainties. And again, here, same thing, I would argue. You start to see actually that these data points, point by point, are of similar uncertainty as the uncertainty in these fits, which means that the collection will have an impact. That is quite clear. So preliminary results for 500 GeV have been shown as well. That paper is in preparation, advanced stage of preparation. Should come out not too long from now. And maybe just to give one more example and work it out a little bit more for dijets. So where we saw these different sign topologies on the previous page, in this case, it focuses on an acceptance region that is truly more forward. Well, so what you see here is X distributions. Those are not to be measured, of course, but you can nevertheless simulate them easily. So what you see is that as these two jets become more and more forward, you actually separate, well, at Born level, these two kinematic regions. And of course, if you then measure the asymmetries, you get sensitivity to, well, the separate quantum distributions in distribution. Right? I mean, it's again not a clear-cut flavor selective or process selective measurement, but it does provide additional kinematic constraints. And these are the results, again, from RAN9, so a modest sample of 200 GeV, recently published. And of course, yeah, this is interesting. I don't read more into it than what it is, right? Statistically not significant, but it clearly outlines the impact that this data will have in global analysis and reweighting, I think. Okay, so switching a little bit to quark polarizations. Werner went at this already in his talk. Just to remind everyone, why are quark measurements at RIC at all possible? That's all the W's. The leptonic decays of W's, that's calculable, so there's no fragmentation involved. In the end, if you can measure this process, you get direct sensitivity to combinations of ratios of quark-helicities or anti-quark-helicities over quark unpolarized quark-helicities. Of course, this is a leading order argument, and yes, the higher orders are well known at this point. Experimentally, it's a tour de force. Thank you. I should be very quick at this point. What you see here is actually, I would say, almost the completion of that program. So what is shown is the 2013 data in preliminary form still. Also, that paper is actually in advanced stages. Well, what you see is, again, the same thing: statistical uncertainties, systematic uncertainties, maybe not of taste, if you wish. This is our central region. But these are more forward regions, and well, one of the reasons for these uncertainties becoming larger is because tracking becomes considerably more difficult in these more forward regions. That's part also of a driver for a forward upgrade. You want to get to better tracking capability in the forward region, even though it would not be used anymore for this type of W measurement in the future. Okay, so in terms of impact, I think we are now at a stage where if you do statistical reweighting of that set of data, you actually get to well, a rather convincing indication of the existence of a flavor asymmetry also in the light polarized sea. In the unpolarized sea, it's of course long known. Maybe a couple of comments about truth in advertising in terms of the kinematic range. That goes from here to here, roughly. Okay, so look, you can think what you want here, you can think what you want there in the end. But certainly at the region where the driving conclusion comes from, there's no question that the data are directly sensitive. In terms of uncertainties, right? I mean, I mentioned statistical reweighting here. Sure, these uncertainties become somewhat larger if you take into account systematics. I think that numerically is actually the more important one of all of them. You could ask questions about the numerator, so uncertainties in the unpolarized part of distributions, how they propagate. That I think numerically is smaller, given that the uncertainties in the unpolarized part of distributions are smaller by a factor. That's not something which at the moment I think can be done in a truly consistent way throughout such analysis. But again, I don't think that's a leading numerical effect. Okay, so beyond quark and gluon spins, look, I like this representation, but I don't like how we often use it. I think it's a fantastic representation, but at times we go a little bit far with it. It seems to me that at times we plug in a function and then sort of we well, make it go the rounds through this, right? Here, I think, okay. Okay, well, theory may just be ahead of experiment, even though actually many questions do remain. Of course, that's not at all to comment negatively on what truly are initial and quite beautiful measurements that have been made, I would say, with sensitivity to measurements that could give us eventual insight in orbital momentum components by Hermes and Gela, and before in the unpolarized case by the Hera experiments. Nevertheless, I mean, going back to the topic and what was asked to do, I think we are truly very far from reliable insights on angular momentum components from data itself. That's just something that truly still needs to come to fruition, if that is at all practical. Of course, I can ask a very different question, right? I mean, why would I care in the end whether orbital momentum, whether first moment is 0.4? mean, would I sleep less if it were 0.2? Probably not. But I nevertheless want to, or maybe I wouldn't sleep at all, I don't know. I need to think about that. Nevertheless, it's completely clear that such a value is easy to communicate if the path is that you're basically going to make vast progress in understanding many of the internals and the dynamics. That by itself is a good motivation. So even though it may seem like a super simplistic well, thing you can relate to somebody, like your funding manager or so, well, someone else.
It's no one more important.
Yeah,
Well,
much easier.
Look, I mean, if in the end, right, let's say we get up this tree, and well, even for something as simple as orbital momentites, it's completely obvious that even though you would not know how to relate TMDs, you actually better understand quite a bit about TMDs if you want in any reliable way to be able to derive matters from well, the super objects. So you will just learn a wealth of internal dynamics on the nucleon, and that by itself is important. Now, looking ahead, of course, this was about EIC. I think the overall power of the EIC can be summarized almost in one figure, which is basically, well, you will be 2 orders of magnitude smaller in X and 2 orders of magnitude higher in Q squared. We know what that has done in the case of Hera for all accessible parton distributions at that time. In this case, because of polarization, nuclei, and variability in energies, and the way to plan ahead with your instruments, the impact probably in the end will be significantly broader, if not larger. There are, I think, no alternatives to it. EIC is a unique machine. So, well, one case, just to get back to one part where I think one can show that there is impact where you can start to talk about decomposition. So this is the figure from the white paper. There have been some updates to this. Nevertheless, I think it illustrates the point, which is that uncertainties go from a very large value, which of course is a moving target with rig data, but nevertheless will stay quite large in part of the range, to uncertainties that are actually comparable in the case of delta G as well as delta sigma, and furthermore would allow you to draw a line. Where you can do a subtraction. Now, I don't know in what system even that subtraction would hold. Want to comment, Elke?
Yeah, I want to comment on this plot. This is excellent. So even we did it, it is totally misleading because it misses actually the low access population. I really think we should refrain from continuous services.
So how is it misleading?
Well,
because it is only from 10 to the minus 3 and it is only the x and the delta G. What sits at low x is not shown here. And we should
yes and no. I mean, so
okay,
I understand. I understand exactly what you're saying.
and we know the spin sits not at high x.
Well, let's not do that on YouTube.
I really don't think that this is right. It is misleading. It gives the wrong impression to people, and we should not continue showing this. And I would stand to this.
Yeah, so
I mean, we have new versions.
I do not agree. Well, first off, I agree that this is not the end of the story. Okay, let that be completely clear. I completely agree with your comment about lower values of x. I do not agree that at this point in the published literature, adequate alternatives have appeared.
Absolutely.
No, that I actually don't agree with. Okay, so if I take the case for the energy measurement, I don't think that the equivalent egg plot, and yes, it's not the same, is a viable alternative for this particular one.
Okay, fine. As I have done both, I completely disagree. But
No.
it's fine. We can
Is that actually wrong?
No.
No, but it's
No.
not wrong. So
It's not wrong.
okay. It's first of all, it is misleading because the delta G is the old version. So we can do an updated one of this. That is fine.
Yeah.
But that already kind of misleads people. But the other thing is, it is only showing the high X version. Basically, it's a data which it's a compass region which we cover right now. And it doesn't give any information, but if you don't measure below, so there could be a lot of spin sitting at low X.
Sure. So,
Sure, but I mean, on the other hand,
look,
you could argue that the X beta with 0.01 region is still probably the one that's accessible at the EIC in the cleanest way, right? Any information going below 0.01 will have lower Q square. And from that point of view, I think so bad to show that plot. I mean, that's the region we can hope to access now a little bit. We see this large area, and now and we see what in that region the EIC will give us.
I really think it gives a message that if you measure until 10 to the minus 3, you see the spin puzzle, and you do.
Why? Because it doesn't say anything about X more than 0.01. It just says in that regime, I think, in one. And of course, you would always have to add that, of course, this may not be the full thing, but
yes, okay, fine. If you add this caveat to the plot, then I'm fine.
So the integral in this particular range can be constrained exactly.
That is fine, yes, but that is not solving the spin sum rule, which is one of the things which we have claimed we can do.
Sure. At the same time, I mean, look, if you want to go there, a few questions can be asked. I mean, look, if you want to put it in this figure, right, I mean, what we're debating in my mind is kind of two things. One thing is that, okay, I mean, this blue band may be overstating the current knowledge, and the central values may shift a little bit because, of course, we're learning as we go. No debate there, that's just fact. Okay, the second thing, which I think we're now debating, is the lower integration limit of both axes. And that's in essence this piece that would be accessed.
Yeah, and if I have different probes, I can actually access this because I can use digits where I can go to lower Q square because my mass, of course, is suddenly, and that is a plot for inclusive.
Yes. At the same time,
yeah, but your X is still constrained.
If I keep it at Q square. Yes.
No, independent of Q square, because you're the lowest X you can reach.
It's not a triangle anymore; it becomes a square, which you can, because your mass.
Yeah, you can go. You can go arbitrary low in Q square, but you can't go arbitrary low.
That's I agree.
Right. So look, we should continue this maybe afterwards. And I think.
Yes.
The parts will need to agree to disagree, but I don't think it comes to data actually where we disagree all the time. So, okay, look, I mean, the conclusions from this I think are pretty obvious. I mean, DIS data has, of course, given us through smaller values of X, actually the start of this entire renewed interest in the end. The data on proton and neutron targets, they cover a wide range at this point, but not a range that is wide enough. They confirm the Bjorken sum rule, with, of course, the usual caveats at the level of below 10%. There is decent insight in the sum of quark and anti-quark spins by the same token, with the same caveats. So there's initial sensitivity to scale dependence, undeniably so. It gives the best insight at the moment in strangeness, even though that insight I think is quite poor, objectively speaking, at the moment. And of course we've seen what I think is a very promising start of DVCS measurements and friends, right? I mean, it's not only Compton scattering, of course. And associated with that, I actually think that along the same lines, I mean, we should not spend too much time arguing between TMDs and GPDs. Of course, if you want to get to a decomposition, yes, but if you want to get to the dynamics, well, we'll see how that will play out in practice. The Rick spin program has certainly almost taught us all that there is to know right now about gluon spin. We also have, I think, through our W measurements, clear evidence of the flavor asymmetry So it's time to give up any constraints of that form. And there are quite promising TMD measurements that are taught by themselves. There's also the forward upgrade again taught by itself. And at EIC theory, as well as experimental capability and accelerator capability, are essential to arrive at a spin decomposition, or at least a partial one. And that's it. Thank you.
Thanks. Question, comments? Maybe just one comment. So that there are indications that the small X contribution to spin chemistry might be large.
Yes.
But there's also indication that the orbital angular momentum small X is also large and has an opposite sign.
May compensate. It may compensate, yeah. Yeah. Completely agree.
And that's at what Q squared is that? I mean, is that, can one quantify what scale that is?
Scale?
Because I mean, it will be functional.
Well, I can argue from the Q square evolution and also from the small X evolution. I don't have a complete number. There are some.
Yeah, I mean, look, with an evolution argument, you know this better than I do, Bernard, but you get at this flavor partition, right? And asymptotically. And if you have one growing distribution, you have to compensate it through its complement. It has to happen.
Right. I mean, the question is where it. I mean, yeah.
When it overwhelms, let's say, anything intrinsic.
It's a question about X. I mean, where. Yes. As we know, of course, any delta G will evolve in such a way that its area gets shifted to a slower and lower X anyway, from just in bigger evolution, right? So at a Q squared of, say, 1000, you will always have a V1 that is sitting, at relatively low X. So the question is, where
does it overwhelm? Yeah.
Well, another question is whether it's a complete cancellation.
Yeah.
Partial.
Right.
I think we have some preliminary results of works where the cancellation is partial. I don't know yet the answer. Between OAM and
Yeah. Okay.
More questions, comments? So thank you very much. Good appetite.